All right, folks, today we're going to look at a torque question. So torque questions, they're either everything's flat and pointing downward or there's some with an angle. So I'm going to tackle one with an angle in it just to kind of give you that extra. Doesn't have an angle, of course, a little bit easier. So let's take a look, read through here. Let's highlight some stuff and then draw a picture and figure what we got. So I have a 1 meter long pole that has a mass of 10 kilograms. Is used to hang a large sign. The sign is attached 20 centimeters before the end of the pole. A cable is used to support the pole and sign. The force in the pole is 1200 newtons and it makes an angle of 20 degrees with the pole. Determine A, the mass of the sign, and B, if the cable could support the setup if the sign was moved to the end. So usually I'd have a picture with it so you can kind of see what's going on, but I didn't draw a picture this time. I'm going to draw one now. That's the way I envision it. So there's like a wall. Then I have a pole out this way. And then the sign or the cable is attached here. And then I have some kind of signs. I'm just going to put like a sign here. That is not a sign. Let's go with a box. That makes more sense for a sign. So let's call that the sign right there. So sign is attached. Actually, the sign's not attached there. Sign is attached in a little bit. So the sign is attached somewhere before the end. It looks something like this. So this will kind of be what your sign looks like. So let's take a look at this. I've got the pole itself, right? And the pole, if it didn't do anything, would rotate like this, right? If there's no support. It would also rotate this way because of the sign pulling on it. And then if the cable is pulled on it, it would make it rotate this way. So let's draw some forces on here. So we know there's a force from the weight of the pole itself. Weight of the pole. And we have the weight of the sign. And then in this direction we have the force of the cable. And remember, weights are just forces, so these are also your forces. Alright, so we're going to make this our pivot point. This makes the most sense. You could set anywhere like we talked about in some of our other examples, but this one makes the most sense. So the pole itself is going to rotate around that, so it's going to rotate in this direction, which we've declared as positive, but you may take this in university or college and be negative. Doesn't matter. If that's positive, then this one will also be positive. But if your professor or instructor says otherwise, then it'd be negative. No big deal. Just goes in the opposite direction. And the cable would pull up on this, so it would make it rotate in that direction, which we call counterclockwise or negative. If these were considered negative by your instructor, then these would be positive. It all balances out. So this is the static torque situation where we have to look at the torques, and we know that it's not going to move. So we have torque from the sign and torque from the pole that are both going clockwise, and then torque from the cable is going counterclockwise. And we know this is going to be 0 because it's not going to rotate. So let's do some substitutions. Torque is, remember, force times r perpendicular, so that'd be force from the sign, r perpendicular to the sign, plus force from the pole, minus r perpendicular of the pole, minus force of the cable, times r perpendicular of the cable. And then we'll make one more line of substitutions. The sign is mass times mass of the sign times gravity, times r perpendicular, and then these little s's just stand for sign. This is mass of the pole, gravity times r perpendicular of the pole, minus the force of the cable, and it's not a mass, so it's just going to be force of the cable times r perpendicular of the cable. And we have the mass of the sign, the mass of the pole. We know the mass of the pole. We're going to figure that out, 10 kg, so we have that. And we know this whole pole right here, from here, oh, that's not very straight, from here out to the end is 1 meter. So the weight of the pole is always centered in the middle of a normally distributed beam, or like straight even beam. So the r perpendicular for the pole is simply half of that. Now the r perpendicular for the sign, move that s down a little bit, r perpendicular sign is how far away the sign is right? So it makes a 90-degree angle. How far away the sign is from the pivot point. And the whole thing is 1 meter, but it says it's attached 20 centimeters short, which is 0.2 meters. So 0.2 meters shy of 1 meter gives me a distance of 0.8 meters. So sometimes people have a little bit of confusion with this because they forget to move it in, but it's 20 meters short of the end, so it's 80 centimeters or 0.8 meters. The one that gives people trouble, of course, is the cable. So let's just draw the cable by itself over here. So this is our beam. Actually, I'm going to do part of it over here. Erase that. So you remember the R perpendicular always goes from the pivot point to where it meets whatever that force is, so they meet at a right angle. And you just have to draw it from the point till it meets up here at a right angle, make a right angle triangle. And I want this side. Well, this long side of this is 1 meter. This angle is 20 degrees. So if I look at this triangle, maybe I'll highlight it in red. I'll do a thick red maybe. So let's go with a pen, make it red, and make it thicker. So this triangle is made up of this. Right there. If I look at that, this side here is opposite of the 90-degree angle. This is my hypotenuse. This side over here is the opposite. So I need to find sine. So sine over 20 degrees equals R perpendicular over the hypotenuse, which happens to just be, in this case, let's put hypotenuse here first. So R perpendicular is equal to hypotenuse times the sine of the angle. So R perpendicular in this case is equal to 1 times the sine of 20. So we have our R perpendicular, so we're all set to plug some numbers in, and hopefully our number pops out at us. So 0 equals 10 times 9.8. Oh, sorry, this is for the, we don't know the mass of sine. That's 9.8. That's 0.8. Mass of sine is 10. Gravity is 9.8. R perpendicular for the pole is 0.5. And the cable we said was 1200 times 1 sine of 20. If I do the math, I get m, the sine, times 7.84 plus 49 minus 410.42. Put these two numbers on the opposite side of the equal sign. And I find the mass of the sine to be, if my calculations are correct, 46.10 kilograms. So most people have trouble usually with the R perpendicular here. So draw it. You can figure out whether you're dealing with adjacent or cos the adjacent or the opposite. So sine or cos, and figure it in from there. And plug your numbers in. So most people have a pretty good time with this stuff. It's just that R perpendicular for these angled ones that cause trouble. Part B says wonders if the cable could support the setup if the sign was moved to the end. If I move that sign out to the end, I'm going to have a greater R perpendicular right here, which is going to make this whole number bigger, and this here cable won't be able to support it. So the answer is no. If this had been a bigger number right here, if this had been 1, then this would be a bigger number to divide, and I'd have a smaller mass. In fact, if it was out at the end, I think the mass would be 36.88. So obviously can't hold as much to put it out at the end. It's like someone on a teeter-totter. If you need them to work, you need them to push them in closer to the middle. All right, that was a bit longer one there. Thanks for listening. If you got any questions, email me or drop in and see me, and I hope that helped. Thanks.